All right, so we're talking about work today. Are you okay?
Yeah.
Think of Charlie horse or anything?
No, hit me like right there.
Okay, because I've been working out.
I could tell.
You're lucky I didn't break your leg.
I was afraid.
So the work thing is a simple concept, but of course it's going to get a little ugly. It's very similar to related rates and optimization problems. The setup is tricky. Once you get the setup, then the rest is pretty straightforward. Okay. So we're going to talk about constant force. That's easy peasy. You did this in physics, right? Have you done work in physics? Yeah. So we'll take a little different approach. I know some of you started twitching when I mentioned work in physics, like you're going to have a seizure or something. But it's a little different when you take a mathematical approach. The hard part is going to be these when we're talking about variable force. And then, of course, your goal today is to become a Jedi Master. No. Because we're going to be using force.
I gotcha.
See how I tied that all together? We're working with force and then...
So do we have to kill all the young ones?
I'm sorry?
Do we have to kill all the young ones?
No. Once he killed the younglings, younglings? What?
Younglings.
He was no longer a Jedi. That's when he turned to the Sith.
I don't think he was a Jedi.
No. I would just want to go on record as saying I'm not endorsing you go somewhere and kill a bunch of little kids. Okay? So, if you're not a Star Wars fan, you have no idea what we're talking about. But okay, so we'll start with the easy stuff. By definition, work is simply force times distance. That's it. And that's what you have to remember the entire time we're working with this. Okay? Force times distance. What's the force on that object? How far did it move? And we're going to make it even simpler because most of the time when we talk about force, we're going to talk about weight. So we're going to calculate the weight of an object, figure out how far it moves, integrate it, done. Anything tough about that? Wow, you are so negative today. It's unbelievable.
You said there was good news.
Well, it gets a little negative, but it's not too bad. Centrifugal, electromotive, gravitational, and the one Luke Skywalker uses. We'll be focusing mainly on force being weight. So we'll start with a simple problem. We want to lift a 50-pound weight 4 feet. What's the work? Which is? 200. I'm not sorry, how much? 200, right? 5 times 4, then add a 0 on that.
He's kind of weird.
Hi, welcome to calculus. And then we got bored. So there's an illustration if you can't visualize what lifting a 50-pound weight looks like. And yeah, so blah, 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 200. By the way, the units there are foot-pounds. This seems bizarre, but it doesn't mean anything. The trouble with this stuff is that you're not going to be able to look at the answer and go, does that make sense? That doesn't, because I have no idea what a foot-pound is. You have no idea what a foot-pound is. So
Question, is
yes.
a foot-pound like the weight of like a foot?
It's a unit of work. So you want me to define the unit? That's like saying, what's a joule? I don't know. It's a...
Or is it 200?
No, not those guys. Yeah, it's the store where you buy groceries.
Just a measure.
Joules, joule.
Oh, okay.
That's a unit of whatever.
Energy.
Energy, thank you. Which is, I don't even know what it is. Or newtons, you know, they're just units. They just describe what we're doing. So work. So we'll have foot pounds, we'll have centimeter, grams, we'll have all kinds of weird ones.
Foot-pounds is weird.
Okay, so is there any problem with that? Are we okay? Okay, force times distance. Simple. Let's make things more interesting.
Negatives.
Yeah, we're gonna bring some trig in. This is pretty much what I said. If you want to read it, I can help you with the big words, but we get that. Okay. So what we're gonna do is we're gonna break a complicated problem into a small chunk. We're gonna calculate the work to move that small chunk, and then we're gonna integrate it to add up all the chunks. That's our force. That's our distance. And then A and B is the number of slices we have, or the pieces of chunks we have. Pieces of chunks? Chunks of chunks. Regardless.
Chunk squared.
Chunk squared, right. Chunks of chunks. All right, so let's start with springs, because they're boring. That's Robert Hooke. He's a good-looking guy.
I'm sure he has a good formula.
Popular with the ladies. And Hooke's law said that we're gonna compress and stretch springs. Okay, so a spring has what's called a natural position. Do you understand what that means? Okay, so it's just if you just hold the spring up, it just hangs at a certain point. You can either stretch the spring or you can compress the spring, depending on what you're using it for. So stretching a spring would be something like, I don't know where you stretch a spring. Trampoline.
Because you can.
Good, right? Then you would compress a spring like in a ballpoint pen when you know, a clicky pen. The spring is compressed inside there. Right. So every spring has what's called a spring constant, which is represented by K. And so the force for that spring is found by taking the spring constant times X. So this is just one type of work problem. Not very interesting, but they do seem to pop up a lot. So I want to kind of go through this quickly, and then we'll get into the fun stuff of lifting weights and dropping things and doing all kinds of weird stuff. Stuff that makes a little bit more sense. Okay, take a 12-pound force and we stretch a spring from its neutral length of 8 inches to 11 inches. Okay, so I got a spring hanging there. It's just hanging down 8 inches, and then I pull it. It takes 12 pounds of force to stretch it down 3 inches. How much work is done compressing the spring from 8 to 13, or stretching the spring from 8 to 13 and 10 to 13. So notice we're going to start from the natural position, stretch it all the way down to 13. Then we're going to start at 10, which is past the natural position, and stretch it down to 13 again. So there are two different scenarios, but they both go really well, or both don't. Never mind. That made no sense whatsoever. Why do I care that it takes 12 pounds to stretch from 8 to 11? What is that going to do for me? It'll give me an equation that will allow me to do what? What chunk of information am I missing about these blue springs?
Find the K.
Yeah, we don't know the spring constant for these springs. Okay, so we're going to do that by doing K times X. So the force required to stretch that spring, a distance of 3 inches, because X is our distance, is given by a K value of 4. And that K value is constant for anything that you do with this spring. Okay, whether you stretch it, whether you compress it, it has that K value of 4. Okay, got the force is 12, the distance is 3, solve for K. Okay, now how do we work some calculus into this? If we're going to go from 8 to 13, 8 is its natural position, so we consider that position 0, and we want to stretch it down to a distance of 5 inches. And so we integrate that simple equation. So Hooke's law is pretty straightforward. You're just integrating the Kx value there over the distance that you stretch it. And like I said earlier, setup is difficult, or is tricky. The integral is ridiculously simple. Okay. Now what about part B? In part B, we're stretching from 10 to 13. What's going to change in this equation for part B? 2 to 5, good. Does the 4x change? No, because the spring constant stays the same for the spring. Okay, so I solved that one. Okay, there we go. Okay, 2 to 5, good. Okay, so that's a distance. We're looking at all those increments of work from the starting value of 2 up to the finishing distance of 5. And I solved that one too. And again, that I don't know if inch pounds makes any sense to you, but there it is. We good with that? Let's do something more interesting. We got a cable. It's 50 feet long, and it weighs 150 pounds. It hangs over the edge of the building and is used to lift an 800-pound beam. How much work is done lifting the beam 20 feet? Why does this problem differ than the very first problem that we did? What's it? The weight or the cable? Cable, right. So in this case, we have to deal with the weight of the cable as a factor involved in solving the problem. Because if you think, you got a picture of this already? Yeah. So there's the picture. As this weight lifts, the amount of cable that's over the edge of the building is decreasing. So every time I pull that cable in, the weight that I'm lifting decreases. Does that make sense? Okay. If I pick up Alex, he's going to weigh 135 pounds no matter how far I pick him up, right? That's about what you weigh, right? 135? 140? What do you really weigh?
270.
Jesus. Boy. I'm not picking you up. You pick up somebody smaller. So I pick up Mary. So Mary, you're like 270, right? You're a little less than Alex, right? So Mary's like around 265, so I can probably manage her. But if I pick up Mary here or here, it doesn't matter. She's going to weigh the same. She's going to weigh the same amount the whole time. But now we strap a cable to this weight, and that cable weight changes as the problem proceeds. So we have to take that into account. All we're going to do is we're going to figure out how much work it requires to move that weight a little distance. And how do you think we're going to represent that little distance? X, big distance, small distance? dx, good. Okay. Blah, 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 blah. Okay. So we got to do a little bit of work here. It's a 50-foot cable that weighs 150 pounds. Therefore, it weighs 3 pounds per foot. And we're going to go with feet because everything is in feet. We could calculate into, whatever. And notice that in this problem, the weight doesn't change. This 800-pound weight is fixed. That is a non-variable force. Are we doing okay so far? Good. So now we just have to take into account the weight of this cable as time goes on. Okay. I start with 150 pounds of cable over the side of the building. And every time I pull some of that cable up, it decreases. And how much does it decrease? It decreases by 3 pounds for every foot that I pick it up. And again, we're working in terms of feet, so I'm calling the number of feet that I pull the cable up as X. Does that statement make sense? Yes or no?
Yes.
Okay, good. And that's our weight, which for our purposes, weight is the same thing as force. And you talked about that in physics, right? The difference between mass and weight.
Yes.
Does everybody understand what I'm talking about? Because this is kind of an important part. How much, if he weighs, what'd you say, 270? If he weighs 270 here, how much does he weigh on the moon? Less, correct. If his mass here is, I don't know what the conversion is, let's, 110 kilograms. If he weighs 110 kilograms here, what does he weigh on the moon? 110 kilograms, right? So mass is universal, weight varies with the amount of gravity. So we're talking about all these problems are taking place on Earth, by the way, just so nobody tries to say, well, if I was on Mars. We're lifting weights on Earth here. And so that weight will satisfy the requirement for our force. Now what we need to do is figure out how far we're going to move that thing. And we're just going to move it a little bit. So let's break this down. This is our weight, which we talked about already, also known as our force. And going back to the very first statement I said, the thing you have to remember is that work is force times distance. Here's my weight, aka force. Here's the distance. Okay, I'm just going to move this weight a little bit. And that will generate a little bit of work. So now why do I use the integral? Because I want to add up all the work that happens in moving that thing from 0 to 20 feet. Does that make sense? Okay, we take a small chunk of work and then we integrate it to add up all that work throughout the entire move. Okay, so I'll go through this quickly because we don't really care. I care about you getting to this point because I think it's safe to assume that you could solve this integral. Could you not? Okay. I'm going to assume that's a yes. Okay. So then, 800 plus 150 is 950, sorry, and then you integrate that. And who knows? Is 18,400 foot-pounds a reasonable answer? I have no idea. So we're just going to go with it. We're going to trust our mathematical skills and assume that's correct.
If we get the setup right, are we going to take the integral on a test, or do you want to?
Depends on the problem.
So it's gonna take the same
For
thing?
me, it'll be similar to what we've already been doing. For the AP test, they mix it up also.
Okay.
Sometimes on the AP test, they'll ask you to work it all the way out to the end, where they might give you a point for the units. Other times, they might just ask you to set it up. Tons of variation.
Is it going to be like with the area problems where you might not have to take the answer version, you might just have to set up?
Correct. Yeah. So the assumption is if it ends up on the calculator portion of the test, no antiderivatives need to be shown, it's F and N. If it's on the Obviously, if it's on a non-calculator, you're not gonna be able to FNA. Correct?
So back when it said, where X is the length of the cable that isn't being pulled, why would it be that if on that diagram, it's the one that's closer to the thing being, it's closer to the top of the roof? Like, I'm just, is it important?
Well, I don't know. There is a good possibility that I screwed up.
Where X is the feet of cable, it was back there.
How's it? Wait, here it is?
Where X is the feet of cable that aren't being lifted. And then if I look at the diagram, X is the first part, so if the cable's being pulled up, X is the first part to go over the top of the roof. I don't know if it has any importance, it was just messing with.
This is right, this is wrong. So if I pulled a cable up a certain distance, X,
Yeah,
then that's what's gonna decrease off the weight. So my sentence is incorrect. It should be the feet of cable that is being lifted. Thank you. Okay. Now, a good one. There's so much going on here that this gets to be a little crazy. We've got a conical tank of, is it water? Yeah.
Molten lead.
Oh, well, we will do problems like that. Because here's the weird thing. When we change the stuff that's in the tank, it changes the amount of work because liquids have different weights. So if I'm pumping water versus pumping oil, or somebody said liquid molten whatever. What'd you say, Luke?
Lead.
Molten lead. Lead's gonna weigh a lot more than water. That's why this is a given piece of information, the density. So we gotta talk a little bit about some chemistry / physics here. Do you understand how density works? What is density?
yeah.
It takes into account the volume and the weight. And so as we change the substance that's in the tank that we're moving, we have to take that into account using the density. Okay, so we got this conical tank, and it's not much different than the related rates problems we did. We're gonna get a similar triangle and do all that other fun stuff. But what I'm doing is I'm taking this entire tank of water, which I think it says it's full, right? How much work is the top of the edge? Okay, so we're assuming the tank is full. I'm gonna take all this water and pump it over the edge. Okay, I don't care where it goes, I'm just getting it out of the cone. I take that big problem and I reduce it to just this little sliver of water. That's all I care about. I'm gonna figure out what kind of work is required to pump that sliver of water out of the tank. And if I can find the work to do that, then I can integrate it to take all the slivers from 0 down to 20. Does that make sense? Okay. I need, going back to the basics of work, I need force times distance. So I need the weight of that sliver of water. That'll be our force. Its distance will be what I called x. And you can define it either way. If I call that x, I'm defining x as the distance that I pump the sliver of water, then what's left here is 20 minus x. You could very well define this as x, the distance from the bottom of the tank, and then it would pump out of the tank at 20 minus x. It doesn't matter how you want to do it. I would recommend, though, that it's a lot easier if you can figure out the x to be the value that you use in the calculation. Okay, what shape is that sliver of water, theoretically? Say again? Kind of, yes. So theoretically it would be a circle, but it has a very skinny thickness. Okay, so we're going to take the volume, so we'll take the area of the circle, which would be pi r squared.
But they're round.
What's that?
But they're round.
Right, good, nice. K r squared, pi r round.
It's like his hard.
Don't be so condescending. Classic joke, especially given that Tuesday's Pi Day. Right, did we talk about that already? Who's on treats Tuesday? You guys got that under control?
And Luke.
Okay, and Luke, yeah, you've drafted Luke since the brownies. Let's try not to have the dog eat any of the pies, okay?
Chocolate pie.
Chocolate pie.
If you figure that, Macdonald's by all the.
I lost track, where were we? Oh, we're calculating the weight. Well, first we'll calculate the volume of that sliver, and then we'll multiply the volume by the density, and we're done with the weight there. Okay, because notice the units on density are pounds per square foot, or cubic foot. So therefore, if I calculate the volume and then multiply by the density, we have the weight. Okay, so blah, 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 blah. here's what we talked about. Pi r squared times dx, because we want a really skinny sliver. And remember, anytime we're talking about a really tiny value, we're using dx for that thickness. And then we're going to multiply it by the density, which is what I already talked about. What's r in this case? It's r, because we didn't specify where we're slapping that disk. It could be anywhere in that cone. And we don't necessarily know the radius yet. Any problems so far? That's of the tank, but not of our sliver of water. Okay, that'll come into play later. Okay. You will not be required to remember the density of water. You will be required to know how to use density, because you'll see problems later where maybe you're pumping oil out of a tank and you'll have a different density for the oil, or liquid lead. Okay. So I define the distance that sliver is going to be pumped as x, and I have the weight of that sliver, and so I'm good to go. I now know the force times the distance. Do you have a question?
Yeah. Well, is the sliver just kind of like a representative rectangle? Like, why do we have a sliver again?
Yeah, it's not a bad idea to think of it as a representative rectangle. It's that little piece of the big puzzle that we're going to solve for, and then add up all the pieces, and we get the puzzle solved.
Okay.
That's a really weak analogy, but okay. That was kind of a big jump. So what happens here? This business, from pi over to the 4, is all the weight of that sliver. Right? Pi r squared is the area. Dx is the thickness, so this is the volume. Times the density gives me the weight. The x is how far I move it. Where'd the 0 to 20 come from? Yeah. It's how many slivers of stuff I have to pump out of there. Now what happens, before I proceed any further, how does this change if I start with the tank half full? What would be my limits of integration?
10 to 20.
All right, 0 to 10 or 10 to 20?
10 to 20.
10 to 20. Could it be 0 to 10? Yes. If I defined x differently, it would be different. But because I defined x as a distance from the top of the tank, I'm starting at a value of 10 and pumping out slivers of water until we get all the way down to the bottom of 20. Question?
Why do you have 20 minus x right there?
That's just the distance from the sliver to the bottom of the tank. Okay, just showing that if you do it the other way around, that you would have to incorporate the 20 minus x. Okay. Then I smartened up and realized that 62.4 and pi are constants, so I move them out in front so I don't have to worry about them in a calculation. What's wrong with that? There's two variables. Yeah. And the r isn't a constant. It is a variable because we can put it anywhere we want. So we got to get rid of one of those. Which one are we going to get rid of? R or x?
R.
Why r?
You can't integrate it.
Because we have dx. Very good. Our integral is in terms of x, so we want to get rid of the r. How do we get rid of the r? We've done this a ton of times. We have similar triangles over there. Okay. So here's my similar triangle there and there, which gets me to that guy. Okay. So where did this come from? This is the height to the sliver over the radius of the sliver is equal to the height of the cone over the radius of the cone. And that's why I got the 20 minus x in. Then I did some math. Cross multiplied, divided, and I end up with r being this monstrosity. Okay? Now I sub that back in. And things get a little crazy. Whoa. 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 Scary. It's better?
Nothing, I just like to complain.
Oh. Can't imagine what you'll be like when you're 45.
All of our parents can be teaching all my kids bad words, so everything I teach my little brother. What?
All I heard was parents and little brother.
Yeah, that's what I've never asked.
You're gonna be living with your parents and your little brother when you're 45?
Family means a lot to him.
I understand.
I'm just reading for
Can you repeat what the x is in that first work equation?
It's the distance that I'm gonna move that sliver of water to get it out of the tank.
Oh,
Okay. I mean, which is ridiculous. You're not taking actual slivers of water and throwing them out of a cone. You're just pumping water out of the cone. But in order for us to be able to solve the problem, that I found that that's a little better way to think of this. Si, senor.
You got 20 over 4. Is that, how'd you get 20? 20 minus x.
Height of the triangle for the sliver,
Okay.
radius of the sliver,
Yeah.
is proportional to the height of the cone
Okay.
over the radius of the cone.
Got it.
Okay. Big jump from here to here. What did I do? I FN'd because I didn't want to square out 4 minus 1/5 x and do all that fun stuff. So I just FN'd.
Can you solve that by hand for us?
I can, yeah. Do you want me to now? Like I'm performing circus show? I can, yes. I'm choosing not to.
Darn.
I mean, I can square a binomial and multiply by x. It's not that bad. Just got the fractions are scaring you, aren't they? Mark.
If I FN into it and left it as 20 minus x over 5, would it work? Instead of like simplifying it more?
Where's 20 minus x?
Oh, I see. If you left this without splitting the fraction there, yeah, it should work fine. You just got to be careful how you type it in. Put parentheses where they're needed and don't put them where they're not needed. I think I said that right. But it should come out the same. And notice I left my answer in terms of pi. The real way to do it would probably be to take that and multiply it by pi to get the actual decimal value of the foot-pounds. But it does turn out to be a nice, pretty answer there times pi. Okay, I know it's really confusing. But again, if you break it down into components, it's the amount of work is found by calculating the work for a little piece of the component and then integrating that to add up all those pieces of work. And how do you find the work? It still comes down to force times distance. Okay. And our force is our weight in most of the problems that we do. We're good. Is there another one on there? Yeah. What's on there now? Leaky bucket? Yeah, we'll do the leaky bucket on, what's today? Friday? On Monday. So on Monday, you've got day 107 to do. On Monday, as I said earlier, we're going to do some damage control. So we'll go over the cross-section stuff. We'll take a look at the work. We will take a look at some of those review problems to start prepping for the Chapter 7 test, which is next week sometime. And you can look at the calendar. This is our last topic in Chapter 7. And then we have one more topic, and we're done.
Wait, so how many more times? One?
Uno más.
So like one more section.
And then we're done.
Yep. And the last section is really easy. It's called L'Hôpital's rule, the hospital. We?
Doesn't sound so easy.
It's ridiculously easy.
Sounds French.
You're gonna, in fact, you'll be angry with me that we didn't cover weight because it has to do with limits. Okay.
You might like that. I'm sorry. That was fun.
Look, I can't tell if he's trying to like sweep the floor or dig a grave.
Definitely not that.
He's a mob guy trying to get rid of another stick figure. That's right.
Looks like Scooby-Doo.
He kind of looks like he's looking at it like, did you take a picture of me?
Draw eyes on him looking back at the camera.
Oh, it's Scooby-Doo. I see
It
it.
looks like he's
Dante, sit down.
Like he's very
Sit down.
No, look, it's
Scooby-Doo
Scooby-Doo.
laying up his ears.
Where's Scooby?
Oh, I see it, I see it. Yeah, turn your head.
This is
That's
his
his
ear,
ear.
that's his nose, and his
the
mouth.
That's Scooby-Doo.
So are you suggesting that that's a picture of a man who chopped off Scooby's head with a shovel?
I think it was Shaggy.
No, best friends.
I think Shaggy.
No, because he'd have a little goatee sticking out of it.
It's just